Okay, I'd like to make a couple of notes about this situation. If we are moving a charge around inside of an electric potential or inside of a voltage, then that's going to be associated with a certain amount of work because we're going to be moving that charge up and downhill in terms of that voltage. So the work will equal the final voltage minus the initial voltage multiplied times the charge. So another way to write this is the work is the difference in the voltage between the final and initial state multiplied times the charge. And by convention, this chapter writes this delta voltage as E. And the E will be called the electromotive force, or EMF. They'll call it that a number of times in the chapter. Next, we're going to ask the question, what if we had to move n moles of electrons within a potential field? First, let's think about Q being the total amount of charge that we're moving. That's going to equal negative, because it's going to be a negative charge for the electrons, n for the number of moles of electrons multiplied times this new constant F, where F is Faraday's constant. And Faraday's constant is equal to 96,485 coulombs per mole. For your information, this is an enormous amount of charge. As a reference, approximately 1 coulomb of charge is exchanged in a bolt of lightning. And this is how much charge is contained within a mole of electrons. If you think of a teaspoon of water, that contains more than 1 mole of electrons. And so then you might ask, wow, how is there so much charge located in such a tiny place? Well, of course, that's because the charge is perfectly, just like so perfectly counterbalanced by the number of protons that are also in that little teaspoon of water. But if you had a mole of electrons concentrated within as tiny of a space as a teaspoon, you can bet that that is going to create an enormous explosion, probably an explosion on the order of a thermonuclear blast. So that just goes to show how much charge is in even just a single mole of matter. It really blows my mind when I think about it. So now let's consider this work equation that, remember, we saw at the beginning of the lecture. The work is equal to the delta G. We also saw that work is equal to E times Q. And we have the formula for Q up here for this transfer of electrons. So this just equals negative N for the number of moles of electrons times Faraday's constant times that change in voltage. For much of this chapter, we are going to want to find this E for an electrochemical cell or battery. One final note, there's going to be an E naught, which is that electromotive force under standard state conditions. And then in that case, you'll have a delta G naught, and that's going to equal N times Faraday's constant times that E naught. On this slide, we're going to introduce the idea of a half reaction. So in an electrochemical cell, we're going to have reactions occurring in 2 different compartments. So it might look something like this. We'll have one terminal there, and it will be connected to another terminal, probably of a different metal, and then these are going to be submerged in two beakers. Again, this is just an idealized representation. Okay, and then there's going to be different solutions inside each one, like so. And then there will also need to be a device called a salt bridge. And the salt bridge is going to allow the free flow of ions so you don't get a buildup of charge in any one of the half cells. So we'll have a flow of electrons either in one direction or another. And that's going to depend on the reactions that are taking place in either one of these half cells. And the direction that those electrons flow is going to depend on this E. The E of the two half cells. Let's see a couple of different examples of half reactions. The first example that the book lays out, a +2 cation of zinc reacts with 2 electrons, which exists in an equilibrium of uncharged zinc metal. Another example might be a +3 cation of aluminum reacting with 3 electrons, existing in an equilibrium with metallic aluminum. One more example, a single proton reacts with a single electron, and it reacts to form half of an H2 molecule. Notice that all of these reactions are drawn as reduction reactions. And this is the convention for half reactions, is to write them in such a way that they are being reduced. This reaction down here at the bottom is called the reference electrode. And there's going to be a certain E0, standard electromotive force, and it's going to equal 0 volts for the reference electrode reaction. Each of these other reactions is going to have their own E0, but this reference electrode gets an E0 of 0 volts. And the other reactions' E0s may be positive or negative. And you can see table 11.1 or 11.2 in the appendix to find the E0s of any of these other reactions. Now the point of half reactions is to put them together to make them a full reaction. So we can put together these top two half reactions here into a full reaction. So we would have, for instance, 2 aluminums reacting with 3 zinc 2+ ions in an equilibrium with 3 zinc metal atoms plus 2 aluminum 2+ ions. And I drew it in this particular order on purpose because it turns out that the total E for this reaction is positive. And by convention, we have to always write a reaction such that E is positive or greater than 0. And I'm going to show you how to do that in future slides.